Let me share my screen. Okay, we studied last time about the conservation of momentum. That is the equation, okay, on the conservation of momentum. Let me give you some equations. Let me give you some examples. Okay, the first example, let's start from the simple. Uh, 6.4. Okay, notice, I want everybody to pay attention here. Notice how do you solve conservation momentum problem? You have to remember this procedure, okay? Conservation momentum problem could be very complicated, okay? I use this 6.4 to explain the procedure to you. It's, yeah, follow it. In the force, you see momentum, every term here is a vector. So force, just like velocity, vectors. So you have three components. Okay, you can just solve the overall force by one equation. If it's multiple dimension, if it's not 1D, if it's 2D and 3D, you have to write down the equation for X dimension, Y dimension, and the Z dimension. Okay, so that's the way you solve it. So you have separate the equations for X, Y, and Z. Just like remember acceleration. When you do acceleration, depends on the dimensions, how many dimensions, or how many equations we have, right? So, okay, let's look at the 6.4. So it's a nozzle. Okay. It's a nozzle. Nozzle, actually, it's a contraction. Okay. Oh, by the way, please attend the class for the rest of several classes. Please attend the class on time, okay? Because I have sometimes I have the announcement at the beginning of the class, okay? So if you're coming late, you might miss some of important informations, okay? Please come on time, okay? We have about, what, today's Thursday, we'll have 2 more classes after today, okay? Please focus in the class, okay? Maybe, I think I will maybe even talk a little bit about the final exam, okay, during the rest of the class. Okay, so the nozzle has what? Inlet speed, so it's a pressure, okay? At the beginning here, 1, at the later part is 2, okay? It says P1 equals 3.7 kilopascal. Okay, diameter 60 millimeter. P2 is atmospheric pressure. Okay, 0, and the diameter is 0.01 meter. Okay, 0.01 meter. Velocity, that's a flow coming into the nozzle. So a flow in and a flow out. Okay. Okay, I guess that's all the information. I give you density. This is air. The density of the air is at 1.22. Okay, 1.22 kilogram per cubic meter. What's the force required to hold it? That's the flange on the nozzle. Okay, so think about it. Okay, you have flange there. Without the flange, the pipe is going to move. Okay, so the flange is here to holding it, to hold it. Okay, so what is the force required to hold this nozzle in place? Okay, first of all, do you have any questions in terms of the problem statement? Okay, so try to understand the basic physics here. So you have the flow, okay, flow into it, okay. Then the flow actually changing speed, right? You know, the diameter changes, the speed changes, okay. And then actually this nozzle will be pushed away, okay, if nothing holding it. Okay, so right now the flange is used to hold it. So you need to, as an engineer, you need to calculate, hey, the required force need to hold it. That's how I design a flange to make sure it's strong enough to hold the thing, right? Everybody? Okay, this is the fundamental of conservation of momentum. Momentum, it's just like that. The change of speed will result into forces. Okay, there will be a force here. Okay, that's why you need to hold it. You need a force to hold it. Okay, so what is the force required to hold it here? Okay, now in the chapter 6, conservation of momentum problem, you need to draw free body diagram. Okay, you see, you did directly dealing with the force, right? Let's just come back, just like we come back to the chapter 3, all the problems you need a free body diagram. Okay, chapter 4, you probably don't. It's acceleration, velocity, pressure, Bernoulli's. You don't need a free body diagram for some of the cases. But chapter 6, we come back to conservation momentum. So you need a free body diagram again. You're dealing with forces, okay? So your body, free body diagram, your body is this nozzle, FBD, okay? Okay, it's nozzle. Okay, so what are the forces? So you draw the diagram. Okay, you draw the object. Okay, notice I didn't draw the flange. Flange is the force we need to calculate, right? So I detach the nozzle from the flange. What should I do? You still remember we talked about this a lot in chapter 3. And you detach your object from the support.
Tension?
Yes, apply a force. I don't know what kind of force is there. Okay, don't say it too early, Joshua. So it may be positive, maybe negative. I don't know. Okay, that's not to assume without any proof. Okay, so but what I pretty sure, what 100% sure I know is there should be a force required to hold it. So let's replace the flange by a force. Let's say we have a force. I don't know the direction. Let's assume it's positive. Okay, don't spend too much time thinking about which direction of that force. Okay, if that's unknown force, put an arrow in the positive direction. If the calculation turn out to be the force have been negative, that means the direction is opposite as what you specified. Okay, that makes sense. That's my way. Okay, I think that's easy to implement. Okay, for unknown force, put any direction actually is fine, but why not always we put it in the positive direction? Okay, it would turn out to be maybe negative direction, that's fine. Then if the calculation tell me is a negative value of f, then that direction is opposite to what I just draw down. Okay, so that's the force we need to calculate, the force we need to hold this flange. Okay, it should be go around the entire nozzle. Okay, but I don't know how to draw it, so I just draw, hey, that's my force, positive direction. Okay, other forces in this problem? No weight here, weight is neglected. Hey, work with me, guys.
Will there be a resultant force where the flow touches the angled part?
The resultant force, the flow touching the angle part. Well, you have pressure, right?
Yeah.
The force, it's the motion. You haven't calculated that force yet, right? The motion is not a force yet, unless you do the calculation. But right now it's a motion. Momentum, you see, motion is included in the momentum terms. You have velocities. But what I'm asking is the direct force. Remember we did the chapter 3, right? What other things would cause force?
Weight.
Gravity.
Gravity is negligible. We're not
Oh,
considering this problem.
Yes, sir.
What other information? Look at my drawing, the letters I put it down there. Okay, which letter will result in a force? Same way we did in chapter 3. Remember, you can forget those things, right? Which letter here? I have letters right down F. Okay, I already drew it here. Rho, P, D, P2, D2. These are what I wrote it down.
Would it be P2? Because when you have that pressure drop,
That's right.
it's like a jet kind of a force.
Yeah, because you have pressure there. Pressure will result in a force called pressure force. Right? Pressure basically is a force per area. Okay, if you have a non-zero pressure, there will be a force. Do you agree?
Yes.
Do you agree, everybody? Okay, so you will have a pressure force on the inlet. This is the inlet, this is outlet, right? You have a pressure force on the inlet. FP. Okay. We did this in chapter 3. Okay, please try to remember. Okay, need to practice to remember the earlier knowledges. Okay. Is that what we did?
We pretty much tell that it's going to be a negative force. That the force holding it is a result, is a opposite of what's pushing it that we just drew.
Yeah. I agree with you, but don't worry about it. It's not certain. Let's calculate it to see if it's positive or negative. See my point? I specified the positive, not necessarily right. It could be negative, right? I specified the positive x direction. Let's see the calculation. If it turns out to be f equals to a positive value, that means it is a positive x direction. If it turns out to be f is a negative value, that means the direction I put it on there should be opposite to the reality. Does that make sense? I don't want you to spend too much time in the beginning to think about the direction of the unknown force. Maybe wrong, okay? Maybe what you think is not complete, not thorough. Okay, let the calculation tell you what is the direction. Okay, that's always I emphasize in this class. Let the math tell you. That's more certain. Okay, everything you say as an engineer has to be certain, has to be correct. Okay, very careful. So let the math tell you, right, Josh? Do you see my point?
Yeah.
Yeah. Okay. I understand it should be negative, and maybe the other side. Okay, but let's see how it goes. Okay, but for solving the problem, you need a free body diagram. You need to place an arrow on the free body diagram to represent that force. Okay, so let's place it as a positive x. But for FP, I know the direction. Do you? The FP1 basically on the inlet. Right? That's I'm certain it is going to the surface. Okay. Everybody, any questions? Anything unclear to you? If you see a pressure, you need to have a pressure force. Okay, that makes sense? Okay. How about outlet?
0.
0. So do you need to draw it? Yeah, come on. I don't think you need to draw it. It's 0. So it will be 0 force, 0 pressure force. Okay. But I want to focus on here. Okay. Next time you will see a problem non-zero at the outlet. What is the direction of that pressure force? That one you need to be certain. You cannot have too many uncertain direction. The reason I put F, I'm not sure, because F is what we will calculate. It's unknown. Okay, but pressure force should be the known value. So you need to be certain what the direction of pressure. FP2 should be this, if it's non-zero. Although the flow direction is from left to right. But the pressure force is always normal to the surface and going into the surface. Do you agree? We talked about it in chapter 3. You always feel, doesn't matter the flow direction. If there's a non-zero pressure, you always feel something pushing it. Okay, think about it. Your face is the surface of the outlet. Okay, your face, you're there. I pretend you are the surface. If you have a non-zero pressure, do you feel something pushing your face? Do you? If it's a non-zero pressure, no matter what the flow direction, separate, think about separately, pressure and the velocity, two things. If there's a non-zero pressure, will you feel it?
Yes.
Yes, you are the surface, you'll feel it. You feel something pushing your face. Okay, that's why the direction, if it's pressure force, is always normal to the force. Oh, I'm sorry, normal to the surface. Does that make sense? Please make sure you know the direction of the pressure force. It's independent to the flow direction. Okay, independent to the flow direction. Yeah, those things you have to make it 100% right before you can actually solve a problem. Okay, but in this case, we don't need to have it. It's because it's zero in this case, atmospheric pressure. Okay, I guess that's it for the forces. Okay, you see, this is the dynamics, right? Fluid dynamics is also dynamics. Okay, statics and the dynamics. I think it's key to draw the free body diagram. I feel you didn't get enough training in the 201 or 202 or 203. Okay, on drawing free body diagrams. Okay, that's why it hurts you in later classes. Okay, but it's a time to learn. Okay, time to learn here. Okay, so for momentum, you also need to draw another diagram called momentum diagram. Okay, free body diagram and momentum diagram. It's a separate, independent. It's, like I said, you draw all the forces to free body diagram. Then draw all the velocities, momentums in the momentum diagram. Can you do that? Can you just follow me step by step, follow me to do it? And do it the same way in the test. Okay, can you do that? Okay, now it's just you have it's engineer, you have to follow the procedures. Okay, so it guarantee you get the solution if you follow the procedure 100%. Okay, that's the philosophy of being an engineer. Okay, so momentum diagram. Can you draw the object like this? I think everybody can, right? Same object like in the free body diagram. Okay, in the momentum diagram, you just write down all the momentums. Momentum also is a vector, as I said many times. M dot V, okay, momentum is a vector. So it's okay to use arrow to represent each momentum. You just can treat it as vector. You treat it as force. That's one of you said it. Oh, you have velocity as a kind of force. But we draw this in the momentum diagram because they are momentum. Their momentum is not force yet, okay? But momentum, it is force, that's true, okay? But when you solve a problem, you draw it separately. Can you do that? Conservation of momentum problem will become really complicated to some of the students if you never attend the class, okay? How many of you attended today? Let's see, 13, okay, 14, okay. It's benefit to you to attend today's class, okay? Momentum, so you have how many momentum you have? I think in this problem, you have a momentum in and a momentum out, okay? If you have multiple momentum out, you draw multiple momentum out. For this one, you have only one momentum out and one momentum in, okay? Draw it. This is the momentum in, mass flow rate in times velocity in, okay? Treat the whole momentum as a vector. That's why you can use an arrow to represent it. Then the momentum out is here, okay? You have to follow the direction of momentum, okay? Not the pressure. Pressure force is always facing, pointed to the surface, but momentum is follow the flow direction. Momentum out, velocity out. Okay, so I will grade it. I will give points for drawing this two diagram if it's a conservation momentum problem. Okay, I will give points. I give a lot of points, maybe 2-3 points each diagram even. Okay, in the final exam. So complete the drawings. Okay, don't miss any force, any momentum. Okay, the reason I want to draw these two separate side by side is the next step. You need to write down the equation. Very easy. Okay, write down the equation. Put an equal sign here between the two drawing. Can you? Okay, equal. So you will know the summation of force will be equal to the summation of the momentum. That's your fundamental conservation of momentum. Okay, so the left-hand side of the equal sign. I'll ask you to do experiment to verify theory, verify equation. I'm really serious about the equal sign. Okay. Okay, all the engineer, previous scientists, what they develop the equation theory is the equal. They have to prove something equals to something. Okay, so very important. So in this case, conservation momentum, summation force will be equals to this momentum out minus momentum in. Okay, I think you should easily write it down. What is the summation force here? So this is, let me ask you this, is this 1D or 2D or 3D problem?
One dimensional.
1D, right? Both of you agree it's 1D. So if it's a 1D problem, you have only one equation. Okay, you have only one equation. Okay, so what are the forces? Tell me. Summation of force. Put all the force together for the 1D. F plus F P1. Since you specify the positive direction of both of them, it will be both of them positive. Okay, can you write down this? Can you do this? Okay. Momentum out minus momentum in the right-hand side of the equation. So what is the momentum out? So probably you want to write mass flow rate times velocity. How many mass flow rate? Do you have a different mass flow rate inlet and a mass flow rate outlet?
It's the same.
It's the same. So let's just use one m dot, right, to represent both in and out. Mass flow rate at the outlet, let's say V2, right? Because we specify section 1, right? Minus mass flow rate at the inlet, V1. Okay, be careful here. I want to talk about the sign. Okay, remember everything I said in this class. Okay, did I start recording? I think I did. Let me see. Yes, I have recording here. Okay, remember everything I said here. The direction here is very important. Okay, the minus sign here, that's from the equation. Mass flow rate out minus mass flow rate in. Okay, when I talk about this general equation, mass flow rate out minus mass flow rate, that minus is always minus there. But for each term, this out and the in momentum in out minus momentum in. I'm sorry, I said mass flow rate out. It's momentum out minus momentum in. Okay, the negative sign, the minus sign is always there. But for each term, it could be positive or negative. Okay, because each term are momentums. Okay, they are vectors. It has direction. I want you to remember what I say here. Everybody, I didn't see much of the camera here, your face here, but are you there? Okay, so each of the term could be positive and it could be negative, depending on the direction you draw on your momentum diagram. Okay, it could be negative if the flow is opposite direction. It's possible if you have a addition flow into the system. It depends, right? It really depends on the direction of your velocity. Okay, in this case, are they both positive? Momentum out and momentum in, are they both positive?
They're both positive,
Yes.
but
Yes.
one negative in the calculation.
No, this negative sign is the minus sign in the equation. It belongs to the equation. It doesn't matter. You have positive momentum or negative momentum. This is the equation. The equation is out minus in. Okay.
They're positive and equal.
I don't know about equal yet. Okay, but positive. But
They're
I
both
think
positive,
they're
so you
equal.
could factor out the m dot.
Huh? What did you say, Dylan?
Could you, I mean, since they're both positive in this equation, could you factor out the m dot?
Can I pack out what?
No, I was saying since they're both positive, could you factor out the momentum?
Yeah. I can factor out the mass flow rate, right? Is that what you say?
Oh yeah, the mass flow rate.
Yeah, mass flow rate. Yeah, I'll do it later. It's a calculation. I don't care. Okay, follow me. The concept here. I want everybody fully understand how do you write everything correctly. Every line, every letter, write it correctly. Okay, the sign. Often students have problem with the sign in conservation momentum problems. Okay, they always make mistakes. Okay, just remember this minus sign is from the equation. Okay, the equation has a minus sign. It's out minus in. That's why I have the minus sign there. But for each momentum out and the momentum in, it could be positive and it could be negative, depending on the problem. Okay, the negative sign is already there, but if the momentum in, it is negative, it will be negative minus, you know, it's a minus. It will become positive. Okay, in the calculation, it could be. Okay, if the momentum in is negative. Okay, if the momentum in is the opposite direction as the x direction, it could be. Although in this problem, it's not. They are not. They are both positive because look at the arrow from left to right. That means it's positive x direction. Okay, so that's m dot v2 minus m dot v1. Okay, I want to make it very clear to use this very, very simple problem to make it very clear to everybody. Later, you could see negative m dot v2 minus m dot v1. It could be, or you could see negative m dot v2 plus m dot v1. It's also possible, depending on the reality, what the direction of the momentum. Okay. Now let's look at the calculation here. Okay, this is the equation without even knowing and what we want to calculate. Okay, now let's look at, is our unknown in this equation? Okay, now if you 100% sure your equation is right, now we just stick with the equation. Okay, just look at the equation. Start from now. Okay, so is our unknown in this equation? What is our unknown?
F. The first
F,
four.
that's a force required to hold it. Okay, it is in our equation. Okay, that's good. I'm happy it's in my equation. Good. So what do I need then to calculate F?
Move your FP1 to the other side and
Yeah, I will move, but what do I need? Overall, the bigger picture, what do I need?
The mass flow rate.
Yeah, I need a mass flow rate, I need the velocities, and
So,
I need
yeah.
the FP1.
I was gonna say move it and then convert everything into units that you know, like row, area.
Don't think too much yet. That's what I stop you there. Why don't you just answer your question step by step, gradually goes to the detail, okay? Don't go to the detail in the beginning. You always like to go to the detail, density, times, or in the beginning, don't, okay? You have, think like a project manager, okay? Overall pictures, what you need. Then you can let your employee to find out each individual, okay? See, that's how you work as a manager, right? Okay, so you need everything in else in this equation. So let's look at one by one. Do we have it? Okay. Do we have FP1? I see you not, right?
Yes,
Some of you.
indirectly.
Well, yeah, you can say indirectly, but it's easy, right? FP1, what is FP1? Let's see. Can you give me an expression for FP1?
P1, A1.
P1, A1. Yeah. Okay. Do you know P1? Do you know A1? I think I have P1 here written. Okay. Do I know
Yeah,
A1?
yeah, A1 is power over 4 D1 squared.
Exactly. Okay. I'm good. I know I have it. I feel good. I have this first term. Okay. I can write it down here. Okay. I know. You can ask your intern to find the value for you, but I know I have it. I have P1. I have A1. Okay. Good. And that's then the bigger question is now the right hand side. Do I have any of them?
You can convert the mass flow rate to
Do I have a mass flow rate? Is this given?
no.
That's why I asked, do I have anything on the right hand side?
No.
Okay, no. Okay. So what's the strategy here?
Convert what you can and see what's left, I guess.
Okay, the strategy is try to find out the mass flow rate or velocity. Okay, let's write it out, the mass flow rate. Maybe that will give me a hint. What is the mass flow rate? What does it look? What's the equation for mass flow rate?
Density times area times V1 times velocity.
Okay, can I use the inlet area, A1 times V1?
Yes.
That's my mass flow rate. Now, Dylan, I can group them together, right? Factor them, m dot times V2 minus V1, right? Is that right? Okay.
Yes, sir.
Okay. So when you look at this right up, what do you really need to find out? Do you have density?
Yes.
It's given. Do I have area? You already said it, right? You already did
Yeah.
it previously. Okay. So what does this problem become? If you're a manager, okay, you're solving a problem. You have a couple employees work for you. Okay. Now you're a manager, you need to tell people what to do. Okay. So what does this problem actually become? In the beginning, you want to solve F, but look at the equation. What do you really need to solve? Yeah, velocities. Okay, now the problem becomes to solve velocity. So if you know the velocity, if somebody give you the velocity, then maybe you can ask your engineer, hey, engineer one, come here, tell me what is the velocity. Okay, so if he give you the velocity, you're as a manager, project leader, you should be able to figure out F immediately. Is that right? Everybody? Okay, I think sooner or later you're gonna become a manager, right? If you survive as an engineer, eventually you become manager. So you need to have a big picture, okay? Instead of just always try to density times velocity, what's the detail leave to the engineer, you become a manager, right? So the goal become to find out V1 and the V2, okay, for this problem. Okay, so what principle you are going to use to find out the V1 and the V2, find out the velocities? Think about it. Now you have a weaponry so far. You have chapter 2, chapter 3, chapter 4, chapter 5. This is chapter 6. So which weapon, which equation is more appropriate to find out velocity?
Bernoulli?
Yeah, do you agree? I hear two of you say Bernoulli. Right? Bernoulli, see, remember Bernoulli has pressure and the velocity in the equations. Okay, So maybe that's the hope. Okay. See, I'm just trying to show you how to solve a problem. In the test, final exam, 2 hours. You have 5 problems, 24 minutes for each problems. You really need to have a thought process correctly. Don't waste any minute of that 24 minutes. Okay. So that's right. 2 of you answered it. I'm going to use Bernoulli's then. Okay. We start with the conservation momentum. Then I see unknowns in my equation. Then I need to use other principle. That makes a comprehensive problem. Is that right? Comprehensive. So-called final exam is always comprehensive, right? So if you combine multiple knowledges, it becomes comprehensive. Okay. So I can draw it again here. P1 is what? 3.7 kilopascal. P2 is 0. Okay. So can I write down the Bernoulli between 1 and 2? Maybe it's still not direct, but at least that's the direction. Bernoulli, write down, please. Okay, let's make it a 2-point quiz here. Okay, you do it for me. Oh, it's not appropriate. It's all on the textbook. Everybody has a textbook. No, forget about it. Let's just do it. Okay. So Bernoulli, P1 over gamma plus Z1 plus V1 squared over 2G equals to P2 over gamma plus Z2 over V2 squared over 2G. Okay, write it down before you even think about it. Do I have enough information to solve it or not? But write it down. Let's see how it goes. When you write it down, it will be more clear to you. Okay, you have something to look at. What do you have and what you don't? Okay. Everybody follow me? Is a procedure? Everybody, did you? Is that good? Understandable? Okay. Okay. Good. I want you to be better, okay? Not only for the fluid mechanics, but for overall general problem solving, okay? You need to have that skill to be a good engineer. Okay, now, any zeros? Can you see? After Bernoulli, always the step is to get rid of some terms, right? Make it easier to solve, okay? So any zeros here? Or anything we can cancel?
Z1, Z2, P2.
Yeah, Z1, Z2 not necessarily 0, but they can cancel. We can cancel. They're the same. It's a horizontal pipe. We can assume they are the same. There's no difference, right? Z1, Z2. Good. Anything 0? I heard somebody say P2, right? It's on the written there, right? Atmospheric pressure. So P2 is 0. Oh, good. At least we reduce the equation into 3 terms. Anything I have? I think I have the pressure. Okay. 37.
P1.
Yeah, P1. Exactly. That's what I'm about to write down. 3.7 kilopascal. Be careful. You cannot put in kilopascal into the equation. You cannot. You have to put pascal into the equation. Okay. So remember what I said here. Everything, please remember. Very important to you. Okay. Gamma. Rho G. 1.22 times 9.8. V1 is my unknown. It's good to in there. Okay, 19.6 equals V2 squared over 19.6, right? 2 times G, okay? That's what I end up with, okay, right now. Okay, so let's say if 20 points, if the final exam is this problem, 20 points. Let's see how many points you get from these points. Okay, let's say here, if you have the drawings here, let's say 2 points each for each drawing, maybe there's a 4 point here, you already get. Okay, I'm probably give another 4 points on show me the correct equation here. Okay, I want you to expand the equation real well. Probably I give you 2 points on here. Okay. Okay, now it's 10 points. You already get 10 points. If you write down the Bernoulli equation, I think probably I give 4 points with the correct reduction. Okay, 4 points there. and find out the velocity V1 and the V2. Maybe another 2 point each. Finally, substitute the V1, V2 into the final equation to find out F is another 2 point. Okay. If I said, hey, Dr. Zhang, I have out of time, I stopped at here. How many points you got? No, it's possible,
Stop
right?
before you
Yeah,
find the numbers.
Before my number, I write down everything. Bernoulli, I make a decision which are zeros, which are canceled. Then I substitute the no value in there and write down the equation like this when I reach to this point. Okay.
It's 14.
There, yeah, 14 point. It's possible out of time, right? I'm out of time. I don't have time to calculate it. Okay. You already got a 14. If you ever problem get 14 points, 14 times 5. 70. Okay, you already get 70 out of 100 in my test. I see the quiz number 10. I give maybe a couple points for some of you, okay, because I regraded. Okay, but look at what you got. 2 out of 10, 3 out of 10, 4 out of 10, 5 out of 10. Okay. I don't want to see that, okay? I want to see 7 out of 10, 8 out of 10, okay? For every problem you do, I give you to do. Okay, that's how you get there. So don't worry too much about the detailed calculation, what times what, okay? This 14 point is only 4 lines of the writings. A join, 2 line here, 1 line here, 1 line here. 4 line of writing, okay? That's why I want you to be in, that's engineering writing, engineer writing, okay? Every sentence write down there means something, and for people to understand, for your record, okay? Did that make sense, everybody? I want you to be an engineer, and sooner or later you'll be a manager, okay? That's the manager's job, basically. Hey, intern, go calculate the V1, V2, F for me, okay? Indeed, I don't want to spend any time I'm doing this, okay? It's in the textbook results. Okay, but you need something addition, right, to find out V1, V2, which is conservation. Maybe I give 1, 2 points. Maybe I here I give 3 points here. I get 1 point. You say, hey, V1, A1 equals V2, A2. Okay, conservation math, right? Is that right? But understand this, right? Flow rate the same. Okay. So you want to substitute this into this equation. Okay. So you have 2 equations, 2 unknowns, right? V1, V2, you have 2 unknowns. Okay. Then you can calculate the V2 and the V1. So these 4 points basically need some calculation. Okay. But hey, that you can do. It's easy. Okay. Do you know A1, A2, by the way? It's given, right? Diameter. 0.06 meter, 0.01 meter, the diameter. So you know A1, A2. Okay. Is that right, everybody? Do you agree? V1, A1 equals V2, A2? Okay, can you substitute this, one of the equation here into this? V1 can be equal to something V2, right? Just substitute there. V1 here squared become V2, something V2 squared too, right? So you have only one unknown V2, you can calculate it. Is that right, everybody? Everybody? Okay, okay. So that's how you solve this problem. So yeah, here, one more point I want to make here is when you see this equation, Bernoulli equation become V1, V2 in both equation, in just this equation, there are 2 unknowns, right? So you think I need another equation, right? I need another equation. What equation do I need? Of course, conservation mass. Quickly, you should spit out, right? Conservation mass is velocity. Okay, I need that equation too. Okay. Any question to this problem? I'll give you the value. Final force is what? Let's see. Let me give you velocity first. Velocity is 2.16 meter per second. And the velocity 2 is 77.9 meter per second. And the force is 9.9, negative 9.9 Newton. Okay. It is negative, Josh. Hey, it is negative. You're right. What does that mean, negative?
Your arrow's in the wrong direction.
Yeah, the one I draw here is wrong direction. It's opposite. Should be goes to the left. Okay.
Yeah, I was just looking at it at first, and I knew that because it wasn't moving, the sum of the forces in the x would equal 0. So I like to draw. Say I know this force cancels this force, so I know I have all of them.
Yeah, if you draw the other direction, it's okay. I don't limit you on doing that. If you initially draw the force to the left, you know what will you get? You will get a force positive 9.9 Newton. Okay. If you specify your force to the left, you will get a positive 9.9. Then that means your direction here you specify is correct. Okay, but for me, I don't like to spend time thinking what's the real direction is. Sometimes more complicated problem at the beginning, it's hard to imagine what is really the direction of the force. Okay, for those cases, I don't want to spend any time on there. I have only 24 minutes for that problem. Okay, I just put arbitrary, always a positive x direction for my force. Then let the calculation plays out. It turned out to be negative 1.9. Good, my direction is opposite. Okay, so that's the way I do this problem. Okay, is that good? Any questions to this? Is that good? Hey, I'm asking any question. Any question? Okay, if you don't ask question, I assume you fully understand, 100% understand this. You can repeat, you know, individual by yourself independently. Okay. Well, that's my hope. Okay, that's my goal here. Okay, I want everybody to ace the class. That means everybody can actually solve problems. Okay, they're good. They're good. Hey, honestly, is that good? You know, I always feel you're good. You know, after every class. You know, but the quiz doesn't show the same way. So yeah, please make sure you fully understand. Okay, before we move on to the next one. Okay. But remember, this is a 1D problem. You said it, 1D. 1D has only one equation, only x component. What about it's a 3D problem? You will have separate equations, momentum equation in all 3 dimensions, okay? You have x direction momentum, y direction momentum, z direction momentum equations, okay? You have to solve 3 equations for separately, independently, okay? Actually, we have an example in the textbook about that. It's actually a 3D problem, I remember. Yep, 6.5. Let's look at it.
Okay, can we just, so
Yep.
you didn't plug, so with the conservation of mass formula, you solved to plug it back into the momentum formula, which you set equal to 0.
What
Because
equal to 0?
otherwise
No,
you would have had a velocity variable
no.
that you didn't know and the force that you didn't know.
Yeah, listen. Here, when you look at this equation, don't worry about the momentum. Now I'm in the Bernoulli equation to calculate the V1 and V2, right? When you look at this, do you have 2 unknowns there? You have 2 unknowns, V1 and V2. So one equation for 2 unknowns doesn't work, right? Josh, do you agree?
Yes, yeah.
Yeah, so you need to find another equations relates V1 and V2. Right, 2 equations, 2 unknowns should be able to solve. Is that right? So that give
Yeah,
you
yeah.
give
I
you a
got the
hint.
the conservation mass. I got that part. You saw, and then you solve for one of them.
You solve
like
two of them. Both
well,
of them you can be able to solve V1, V2.
You could get the value from the conservation mass.
You have, if you know V1, can you find a V2? Or
Yeah.
vice versa? Yeah, go ahead. Either equation. You can even use the Bernoulli equation to find, if you have V1, then you can find the V2 too. But it's easy, more easier way is to find the relation in the conservation mass, right? V1, A1 equal to V2, A2. If you know one of them, you should find the other.
Oh, okay, I got you. What I did, I saw with the conservation mass, I saw for the wrote my values down, saw for V1, and then I was plugging it back into the formula that we had F in. But if we plug it back
So
into
you still need
Bernoulli,
V2.
be able to solve it. Okay,
Yeah. In Bernoulli, you anyway, two equation, two unknowns. Remember, two equation, two unknowns. If you have two equations, you can solve the both unknowns. Okay, this is just algebra. Okay, so after you calculate the V1, V2, you need a V1, V2 because in the momentum equation, look at this. In order to calculate F, you need a V1 and V2. Okay, even calculate the mass flow rate, you need one of the velocity, but in the momentum equation, you need both these. Okay. Good. I like questions like this. I'm here to help. They're good? (6.5). It's a 3D problems, but it's, although it's a 3D, you will have three equations, but if you think of the three equations separately, it doesn't matter. It's just the same way you solve, just like 6.4. Okay, example 6.4, same. Okay, so now you have a band. Okay, have a band. So you have two phalanges to holding the band. Again, you have inlet and outlet. Okay. Flow, I think it says 30 degrees here, the direction of the outlet to the horizontal. The oil, I think the oil specific gravity, it says 0.94. It's kind of like oil, it's lighter. Flow rate, it gave you the flow rate. Hey, that's good. This problem seems like a better. 2 cubic meter per second. This is the volumetric flow rate, right? 30 degree. The volume of the band, it can even give you the volume of the entire band is the volume of oil in the band, yes, 1.2 cubic meter. It tells you that it's a trivial problem, a lot of calculation, but it probably is easy. The empty weight of the band. Empty weight of the band is 4 kilonewton. Assume the pressure along the center line of the band is constant at, okay, P1 is 75 kPa, P2 is also 75 kPa. Okay, they're the same. Find the force required to hold this band. Okay, next time if you see any question ask you to calculate the force, okay, you ask, the first thought is maybe I need to 80%, 90% chance that I need to start with conservation momentum problem, momentum equation. Okay, when you solve problem, see the process after you read the statement, you need to identify, first thing is identify which weapons I'm going to use, which equations I'm going to use. Okay, so give you a trick here. If you see something like, oh, okay, ask you to calculate the force required to hold it. Okay, 80–90% chance probably you need to start with the conservation momentum. In other words, if you start with the conservation momentum equation, 80–90% of chance you have the right direction. Okay, which is good. Okay, 3D. What is the force required to hold it? 3D. So that force will be Fx, Fy, and Fd, Fc, right? 3D. Again, okay, if you decide it's conservation momentum problem, draw the two diagrams here. hey, follow the procedures, follow the steps. Okay, you know, after you draw the diagram, I'm gonna write 3 equations. See, you never see people teach you how to solve a problem like this, huh? X. I already have a way to solve a problem. See, that's a guarantee I can solve the problem. I'm filling the blank now, okay, for solving this problem. Okay, so if you prepare a test, you just need to know if conservation momentum, these blocks, can I fill in? Do I know how to fill in those blocks? Okay, did you see my process here? Okay, no problem is easy problem. No problem is difficult problem to me if I know this. Okay, so free body diagram. Okay, again, what is the first thing? Fx, Fy, Fc. Hey, Josh, this one is more difficult to decide what direction is. What the direction of Fy, can you tell? The force required to hold it, see? For more difficult problem, it's difficult to tell. You don't want to spend any second in the beginning of the problem just to think about, you know, what is the direction of the force required to hold it? You know, don't waste that second. Okay. Put an arbitrary positive direction force for your Fx, Fy, Fc. It's a 3D. I cannot draw the third dimension. I use a circle with a dot, means it's positive going out of the paper. Okay, just like an arrow, right? If you have a cross, that means goes into the paper. Okay, I assume the z direction is going out of the paper as a positive. This is basically a top view of the object. Gravity is going downward. Okay, gravity is going into the paper. Is that clear to everybody? Okay, first of all, you need to understand the geometry, the problem statements. Okay, Fx, Fy, Fc. Okay, everyone on the same page with me? Okay, good. What other forces? Free body diagram.
Pressure force.
Okay, pressure force. How many you have today? For this problem?
2.
Yeah, 2 pressure force. FP1. Yeah. So again, the other pressure force, angle, direction, FP2 is point towards the surface, although the flow direction is opposite. Whatever flow direction is, it's independent. Okay, the pressure force is always towards the surface. If you draw this wrong, you'll not be able to solve this problem totally. None of them. Okay. Any other forces?
I got a quick question.
Yeah, Patrick.
So on that previous problem, if P2 wouldn't have been 0, then there would have been a pressure force going back into it just like this one?
Yeah, exactly. You will have another one. I think I drew it, I erased it. Okay, because it's 0 here. Okay. Okay, everybody? Good. One more force you missed.
The Y force.
The what force? Y force?
I mean,
Gravity.
Yeah, is that what you mean, Dalen? Gravity?
yeah.
Gravity, yeah. When you say the engineering way, okay, say it.
Yeah,
okay, say it the
I
right way.
got you.
Okay.
Yeah, for sure.
Gravity is going downward. Okay, let's see. That's how I circle with the cross. That means the arrow. See the back of the arrow. Okay, shooting down. So going into the paper. That's a gravity. It's W. Be careful. It gives me the empty weight, but in this W is not the empty weight. Okay, be careful on that. Later, we're gonna deal with that. Okay. Momentum, that's it. That's all the force, right? I didn't miss anything, okay. Momentum diagram. How many momentum we have? How many momentum we have? We have two momentums. Now this is not as simple as last time I said momentum out, momentum in. Yeah, it is a momentum out, momentum in, but the direction, actually, when you do the calculation, it matters. Of course, I don't have momentum in the z direction, right? It's not moving along z direction. Z is just gravity. Okay, momentum in is m dot 1 v1. Okay, and the momentum out is m dot v2. Okay, and this is the angle, 30 degrees. Eventually, I guess you need to separate the momentum into x and the y direction for your calculation of x and y. Okay. So let's work together to write down the equation. Is that right? There's only two momentum here, inlet and outlet. Okay. The overall value of the outlet is m dot v2. Okay. However, when you do the calculation, it's not on x direction, it's not on y direction. This is x, this is the y, right? So you have to separate, okay, right? You know how to separate if given the angle, right? Okay. Okay, now let's have 5 minutes here. Let's write down the equation. Okay, I have 3 equal sign here. I strongly suggest you do that too. If you see a 3D problem, write down 3 equal sign first. Okay. Okay, now let's look at the x direction. What is the force balance? Summation of force in x direction.
FPN.
FP1, right? Yeah.
Oh, 1. Yeah.
Yeah, it's fine.
Would it be minus FP2 cosine theta minus F?
Cosine 30 degree, right? Why it's minus F? What is FX I draw on the?
There's more the
Look at what I'm drawing on the free body diagram. You basically translate the free body diagram into equations, right? You have FP1, correct. FP2, you put a negative sign. It's because opposite direction. You times cosine 30 degree. Okay, it's a component, right? How about FX? Should be plus FX or minus FX?
Plus,
it'd be
right?
minus that. Yeah, that's what I said. Minus F. I was like, I didn't know. I know there's got to be another one because FP1 equals FP2,
So Josh,
and you only got a portion.
Josh, everything right now here, when you're writing this equation, only thing you want to look at is your free body diagram. Do you agree? Can you do that? Okay. You assume your free body diagram is correct now. You spend time to draw the free body and make sure it's correct. Okay. I just want to convert my free body diagram into my equation.
Okay, so the F of X, put F.
Yeah. So just plus FX. Okay. Just put it down on the free body diagram. That's why at the beginning, I wanted to make sure everybody know how to draw free body diagram 100% correct. Okay. Then you can have something to rely on, something to rely on. You write down the equation much easier. Basically, translate the free body diagram into the equation. Is that right? Summation force. Okay. And that's why I write the equal sign on the borderline between the two diagrams. So the free body diagram will convert into the left-hand side of the equal sign. The momentum diagram will convert into the right-hand side of the equal sign. Okay. Anybody give me the momentum equation? It should be momentum out at the x direction minus momentum in the x direction. Give me something. Just give me everything. Just from the diagram, MD diagram.
The m dot times the difference between.
Give me exactly. Don't tell me the sentence. Give me the expression. M dot
Open
momentum out in the x direction minus momentum in at the x direction. Okay. So give me the expression. Devin, you can do it.
M dot open parentheses V2 minus V1.
The momentum at x direction at the outlet. How do you use the expression to represent the momentum x direction at x direction moment at outlet? Yeah, go ahead.
That would be m dot V2 cosine of our theta.
30, okay. 30 degrees the angle, okay, minus momentum out at x direction minus momentum in at the x direction. Continue, Devin.
M dot 1 V1.
Yeah, that's it. You complete that equation. You get some points there. Okay. With the correct equation, that's the only hope that you can solve it correctly. Okay. Am I missing anything in x direction? I guess that's it, right? Okay, write it down before we can solve. Okay, let's do. I have 2 minutes. Let's do the y direction. Okay, anybody give me the force balance on y direction?
FP2 sine theta plus Fy.
Sine 30 plus Fy. Right? Did I miss anything? I think that's it, right? You don't have FP1. It's only x direction, right? Fy, yeah, it's positive. FP2, right? 2 components. Okay, momentum. That's tricky. I have 1 minute here. Anybody?
Negative m dot. That is the outlet V2.
Mm-hmm.
The outlet of V2, and that's all gonna be times.
How about the angle? Yeah, you're saying it right. Is it sine?
Yes, sir. It's sine because it's at.
Yeah, that's correct. Okay, continue. Out minus in.
Yeah, out minus in.
Okay, in, what is in then? Minus y direction momentum in, what is that?
Is it V1 or V2?
What is the y direction momentum at the inlet going into the system? Is there any?
Would just be 0.
Would it be 0, Dylan?
Yeah, yes, sir.
Yeah, it will be 0, right? It's 0, it's just 0. Don't be afraid. Okay.
I got it.
Yeah. Good. I guess that's the time. Let's leave the z next time. Okay.
So since the inlet was coming in straight to in the x direction, the y portion 0. If it would have been opposite, the x portion would be 0. Do you know what I mean? If it would have been coming in straight down from the y and curving, then
well, why you have a momentum out? Basically, the momentum being separated into whatever momentum coming eventually is separated into 2 parts. Some goes to still live on the x direction. Some become the y direction momentum because of the angle of the bend. That's why in here you have a momentum out at the y direction minus momentum in at the y direction, which you don't have. All right, Josh, is that right?
yeah, I guess what I'm asking is all the momentum from the
you have to look at the momentum separately.
From the inlet is going to be on the corresponding sum of the f of x, since it comes in x. Do you see what I'm asking?
Yeah. See, from an energy point of view, you have total energy going into it. Okay, because of the bend, and it directs your energy into some of them to the x direction, some of them goes to the y direction. That's a big picture. It's although it's not the energy equation, but still you can think like this. You have a momentum coming in the system, okay? But some of them goes to, because of the bend, right? Some of them leave on the x direction, but some being directed into the y direction. But for solving problem, don't need to worry about this. You just separate the equation on the y direction and the x direction separately. Look at separate momentum. Yeah, Dylan, you have a question? You raise your hand.
Yes, sir. I mean, since we kind of went past time, and you said there was gonna be a quiz today, I mean, what do you want us to do?
No, you mean a quiz? I'm out of time today. I don't have a chance to give you a quiz, but maybe next time.
All right.
Okay, I definitely will have a quiz next week. Okay, for you to improve a little bit. Okay.
What do you know what chapter be on? We need to look at chapter 5, or we'll be over this stuff.
How about I give you a quick 10-point quiz for chapter 5? Since I already assigned the homework problem for chapter 5. Okay, so prepare it, maybe Monday. How about that?
We don't have class Monday.
Oh, no, I'm sorry, Tuesday. Yeah, the first class, yeah. Okay, I'll continue on this, and maybe I give.
How many total people do we have in this class? How many people aren't here?
I think I have 17. I don't know how many you have here. How many? We have like 12 here. Okay, so
there's 19 people in the class.
yeah, I see.
In the group meet, there's 20 people, and excluding you is 19. So we have 19 people.
19. I have 3
but only
dropped.
13 people are in the Zoom.
I think we have 3 students dropped from the starting of the semester. So there will be 16 actually total right now. Okay. Okay, I guess that's it for today, and see you Tuesday. So do some practice on chapter 5. Okay.
I have a question that's not